Hello, everybody. We're going to wait a few minutes before we start so everyone can join.
Morning, everyone. Nice to meet you all.
Hello.
Hello, Pablo. All right, so we're going to start now with the presentation of this workshop. Of course, thank you very much for joining us today and welcome to the MAGNO Ecosystem Digital Twin, in which we are going to, of course, introduce the digital twin, the latest developments and advances within this digital twin. So we're going to start this session by briefly introducing the IDENER team and the MAGNO project. Then we will follow with an introduction to what digital twins are and their role in circular value chains. Then we will continue exploring the MAGNO's ecosystem digital twin, and we will perform the real-time simulation with a selected use case. Then finally, the session will end with a question and answer roundtable. So who is IDENER? We are an engineering and technology company that focuses on applying advanced digital technologies with the aim to solve complex scientific and industrial challenges. This company started as a spin-off in 2010 of University of Seville, and after 16 years of existence, we now count with more than 100 employees, and we constitute a multidisciplinary team. Then our overall goal is to develop technologies that not only improve the industrial performance, but we can contribute to human development. As such, you can see here in the below part of the slide some of the IDENER coordinated projects. And actually, the digital twin that we're going to present today is just one example of how these technologies can support data-driven decision-making throughout the whole life cycle of packaging food. So as I was saying, this digital twin has been or is being developed within the MAGNO project, which is a Horizon Europe research and innovation project funded under the Zero Pollution program. This project started in January 2024 and will run until June 2027. and it comes with a total budget of around 4 million euros. So this project brings together partners, actually 10 partners from all across Europe and 2 affiliated entities from Lebanon and from Tunisia, with the common aim to solve or address one of the major environmental challenges facing the food sector, which is plastic packaging pollution. The motivation behind this project is basically to enhance the efficiency and sustainability of the food packaging sector to support the transition to a circular economy. So this project aims to promote the adoption of solutions in order to reduce the impact of food packaging pollution on ecosystems such as soil, water, and air. Among these criteria for these strategies, we have to highlight the innovative, renewable, and recyclable and/or biodegradable materials, the design for circularity in order to reduce material consumption and, of course, to increase the reuse and recycle, substitute harmful substances in packaging formulations, and smart solutions to monitor food quality and extend product shelf life. Moreover, beyond the technological innovation, this project also aims to understand the environmental impacts of plastic packaging, as well as to develop and validate innovative business strategies and actively involve policymakers, industry, and society in the transition towards more sustainable food packaging systems. We've been talking about digital twins in these presentations so far, but what are they actually? So a digital twin is a living replica of a real-world system that uses live or near real-time data to mirror and enable realistic testing. Unlike a database, dashboard, or static model, a digital twin enables a dynamic what-if scenario analysis. The physical system can be objects, processes, or systems, or even imagine an industry, for example. So its key capabilities, so a digital twin is going to be a living data representation of this real-world system, and it continuously integrates data, models, and simulations that are going to support this decision-making. Among its key capabilities, these digital twins can connect real-world and virtual systems alongside integrating multi-source data across the life cycle. Also, they simulate alternative scenarios before implementation, which allows users to reduce resources. Also, they support evidence-based decision-making. So overall, digital twins allow to move from reactive management to predictive and more proactive decision-making. And why are they important for circular economy? Well, circular systems involve multiple interconnected actors and life cycle stages. A digital twin, therefore, enables system-level analysis across the entire value chain. So imagine the MAGNO example. Instead of viewing packaging as a product or waste stream, the MAGNO Digital Twin models the entire circular value chain network, which includes, of course, product design, manufacturing, different logistics processes, the retailers, the consumer use and demand, and reuse, recycle, among others. So as such, the inclusion of digital twins into this kind of circular value chain supports the transition from linear packaging systems to circular data-driven value networks. So let's move on now to the MAGNO's ecosystem digital twin. As I was saying previously, the MAGNO digital twin represents the entire circular value chain, from product design to end-of-life management and material recovery. So the workflow begins with the product design stage, where the packaging solution and its material characteristics are defined. It then progresses through the manufacturing, where the production technologies can be selected depending on the packaging format and the material. Here we have 4 different types of manufacturing processes, and we can choose between injection molding, thermoforming, blow molding, and extrusion. Then the model subsequently captures the logistics stages through the post-manufacturing transport, which is then followed by the food packaging operations. This stage is where the packaging is integrated into the food production process. So after packaging operations, this packaged product is transported then to retailers through the retailer transport stage. Once it reaches the retailer, this module evaluates packaging performance during the storage, which includes as well the aspects related to shelf life preservation. Afterwards, the use and demand stage represents the consumer context and market demand for the packaged product. Afterwards, once the product reaches its end of use, the digital twin follows the reverse logistics pathway through the waste collection and transport, sorting and baling, and post-sorting transport. And then finally, the model represents different circular end-of-life scenarios within the circular end-of-life module. This module includes chemical and mechanical recycling alongside the recovery pathways. So let's explore each one of these modules. This is the product design module, and it serves as the starting point of the digital twin workflow. The purpose of this module is basically to define the packaging solution that is going to be analyzed throughout the value chain. So the first group of inputs that the user needs to introduce describes the general design context, which includes the design country, the package identification, geometry type, and the number of units that are going to be considered in the assessment. Regarding the geometry type, we have been able to simulate or represent 3 different types of geometries, which are rectangular for box and trays, circular for bottles and cans, and random or flexible shaped for pouches or bags. Then the model requires this geometric information to describe the package dimensions. As I said, these specific parameters depend on the selected geometry type, which can be these 3 options. Finally, this last group of inputs characterizes the packaged food product, in which users can define how food-related data are introduced into the model, together with food density parameters, filling level, and the external transport volume per unit. Now the manufacturing module simulates the process by combining material characteristics, process operating conditions, and the production-specific parameters. So let's start with the first group of inputs. These basic parameters, basically, they define the production context, such as the location where the production takes place, and it's going to influence factors like electricity supply or environmental impacts. Then these material properties describe the physical and thermal characteristics of the selected polymer, which are going to determine how the material is going to behave during different stages, such as heating, melting, cooling, or solidification. Then the process parameters and the advanced parameters are exclusive to each selected process. In this case, we have selected, as you can see here, the injection molding process. But if you remember, we could have chosen between blow molding, thermoforming, and extrusion. So for instance, the process parameters largely determine the production efficiency and energy consumption, and are exclusive to each kind of manufacturing option. Then these advanced parameters capture additional process details that are related to material losses, also to moisture management, cooling performance, and the production configuration. These advanced parameters are they allow the user for a more accurate representation of the real industrial conditions. Moving on to the post-manufacturing transport, this stage represents the logistics stage from manufacturing to filling the package with the food product. So first, the user needs to select a transport mode and this selection provides the key operational parameters that are needed to estimate the transport-related energy use, emissions, and environmental impacts as well. Next, we have the extra transport mass, which accounts for the auxiliary logistics materials such as pallets, wraps, and all the handling components that increase the transported mass beyond the packaging itself. And finally, we have transport distance and vehicle and fuel characteristics. The first one, transport distance, define the length of the transport leg and is one of the main drivers of the transport impacts. As the vehicle and fuel characteristics for road transport, that is the one that we have selected, the model uses parameters such as the vehicle family, if it is a van, a rigid truck, or an Arctic truck as well, the size and subcategory of this vehicle, and the fuel that has been selected. So these represent the different transport configurations and efficiency. Also importantly, these parameters that are shown in this slide and for this module are just examples for road transport. So each transport mode is going to require its own set of mode-specific inputs that reflect the characteristics of that logistics system. Now we have the food packaging process, and it represents the packaging activities that are performed after the packaging manufacturing and transport. So this module captures the operational conditions under which packaging is used within food processing and packaging lines. First, we have the packaging process configuration, in which it is defined the type of packaging operation that is going to be modeled. For example, we have tray sealing, cardboard top, bottle of yaw, flow wrapping, vertical form fill seal, horizontal form fill seal, and vacuum packaging. So in our case, since we are working with PET bottles, we would select bottle, but it depends on the kind of product that you want to model. Also, we have here the calculation mode. That is basically the approach that is used for the simulation. So we can select here, we can choose here between basic, we are given the default machine parameters, and the advanced. So we can custom the power and speed parameters. These selections are going to determine how the operational state is represented within the digital twin. And afterwards, we have the energy-related parameters, which characterize the performance and efficiency of the packaging. Parameters that are related to the throughput level and the equipment efficiency are used to estimate the energy consumption and operational impacts under different operating conditions. Now we have the two retailer transport module that represents the distribution stage between packaging operations and the retail point. It basically captures the logistics conditions associated with delivering packaged product throughout the supply chain. And this module works exactly the same as the previous one. Now, when the package reaches the retailer stage, it assesses how the packaging characteristics influence both the product shelf life and the preservation of quality. So this module combines first geographical context with food packaging interactions related to moisture and to oxygen transfer. So first, the user is required to define the country where the product is sold. So this information is mainly used to represent the retail environment and associated regional conditions. Moving on to the moisture shelf life assessment, it evaluates the impact of moisture transfer through the packaging material on product stability and shelf life. So these calculations are based on the GAP isotherm, and they consider material barrier properties, package characteristics, product moisture behavior, and environmental conditions. As I said, this model uses the GAP isotherm, so it requires some GAP-related parameters, such as the monolayer sorption behavior and the multi-layer sorption behavior. And since these parameters depend strongly on the specific food product and storage temperature, they may need to be obtained from experimental data or literature sources. But in the other cases, the user has the other default values as well. Then we have the oxygen shelf life assessment, which estimates the product shelf life based on oxygen permeation through the packaging materials. So these calculations are based on the Fick's diffusion law, and it considers product characteristics, oxygen sensitivity, package geometry, material permeability, and material thickness. So by combining both moisture and oxygen shelf life assessments, this module can evaluate the ability of packaging solutions to preserve food quality during the retail stage, and it supports the comparison of alternative packaging designs and materials. Next, after the retail stage, we have the use and demand module, and it represents the consumer stage of the value chain. Basically, it captures the market context in which packaged products are consumed, and it provides the information required to assess the packaging performance at the demand level. The first group of inputs define the country where the product is consumed and the food category under analysis. Here we can select between beverages, dairy products, meat or fish, fruits or vegetables, etc. In our case, we will be selecting beverages because we're going to simulate a PET bottle of water. Then the next inputs that are required for the user are the demand definition and analysis options. So the demand definition is specified by the number of units that was selected previously in the first module, that was a product design module. Then the analysis options provides additional reporting capabilities that includes also the possibility of generating a more detailed breakdown of the results across the different stages of the value chain. So as a result, this module translates the technical packaging assessments into the market scale consumption scenarios. So now we enter through the reverse logistics pathway. The first step is the waste collection and transport module, and it models how post-consumer packaging waste is collected and transported for both sorting or final disposal. So first, we have the waste collection context that defines the country and population associated with the assessment. So basically, these two inputs are used to estimate the default waste management conditions, such as the transport distances and the distribution of municipal solid waste streams. Then we move forward to the packaging and waste flows, and these use packaging information from the packaging design module and allows users to define the quantities of materials that enters the recycling and residual waste streams. This model also accounts for packaging rejected during the sorting in its destination. That can be either incineration or landfilling. And finally, we have the transport configuration, in which we can characterize the different transport legs that are involved in waste collection and management. Here we include as well the collection to the sorting facility and transport to final disposal. Here users can define transport distances as well as vehicle capacity and load conditions to improve the accuracy of transport impact calculations. So overall, by combining the waste flow information with transport parameters, the module can estimate the environmental impacts that are associated with the collection and transport of packaging waste before their sorting and treatment. Speaking of sorting and treatment, this next stage is the sorting and baling module. And it represents the material recovery facility where the collected packaging waste is separated, compacted, and prepared for recycling. So first, we need to introduce the input material, which defines the amount of waste that enters the sorting facility and the overall sorting performance. This model can use either an overall sorting yield or material-specific efficiencies to determine how much packaging is successfully being recovered. This next group of inputs are related to material recovery parameters, and they specify the target material and country in which sorting takes place. So these sorting efficiencies can be provided by the user if they are known by them, or automatically retrieved from country and material-specific datasets. These advanced options also allow users to account for mis-sorted and rejected materials fractions. Also regarding the baling parameters, they describe how the recovered material is prepared for transport and recycling. This includes the characteristics of the produced bales, such as the purity or density, which ultimately will influence in subsequent logistics and recycling processes. And finally, we have the energy-related parameters that account for energy required during both the sorting and baling operations. And these parameters can be either defined by the user as well or obtained from reference data depending on the selected country and material. Next, we have the post-sorting and baling transport that simulates the transportation of materials after the sorting and baling stage. It is, let's say, it routes both recovered materials and rejected fractions to their respective end-of-life destinations. So as we can see here, the first group of inputs define the destination of recovered bales according to the selected end-of-life pathway. We have selected mechanical recycling in this case, but we could have chosen any other kind of end-of-life path. It also accounts for the destination of rejected materials that have not been recovered during sorting. These next inputs are related to the residual reject, and they allow users to characterize the rejected material through a set of physical properties and the required for the selected disposal or recovery route. In this case, it has been incineration, but it could have been also landfilling. And the last group of inputs, they are these two, and are related to the transport configuration, which allow users to specify transport distances and vehicle characteristics for both recovered bales and rejected materials. In this case, the default values can be overridden to represent the specific transport scenarios and improve also the accuracy of the logistics assessment. And now we reach the end of life of this of the product. So now this module represents the mechanical recycling pathway that is available within the digital twin among the other end-of-life options. And it models the complete recycling process, the complete mechanical recycling process, accounting for material losses, energy consumption, and the evolution of recycled material quality throughout the successive recycling cycles. So the first group of inputs are related to the stepwise mass balance that represents the material losses that occur at each stage of the mechanical recycling process. So these losses are going to determine the final recycling yield. Additionally, these energy consumption parameters define the energy that is required by each processing step, and it enables a calculation of the environmental impacts that are associated with the recycling options. And finally, here, regarding the advanced quality and decontamination, first, we have the material quality, yes, to characterize the contamination level of the incoming waste and the efficiency of cleaning and filtration stages. And it allows the model to estimate the quality improvement achieved during this recycling stage. And finally, here we have the recyclability and quality assessment. And these parameters allow users to track the degradation material quality over multiple recycling stages. So users can define quality retention parameters and recycling thresholds in order to evaluate whether the recycled material remains suitable for closed loop, or they should be directed to alternative end-of-life pathways. And finally, this module, the Health and Environmental Impacts module, provides additional parameters that are used to quantify the sustainability performance of packaging systems across the whole value chain. This module incorporates explicit environmental impact factors and supplementary logistics information that may not be fully captured by the operational modules by themselves. So this first group, the raw materials impacts defined environmental and health-related parameters that are associated with the production of packaging materials. And these inputs account for the balance between virgin and recycled content, the resource consumption, and the direct emissions that are linked to the material production. Similarly, we have something close related to manufacturing, and it captures the environmental performance indicators that are related to the manufacturing stage. It includes the reuse, the resource use, the emissions and waste management. And these parameters are going to help to represent the environmental footprint of production activities in a more accurate way. Finally, the additional transport legs contributions includes the supplementary transport legs that are required for a complete assessment of the packaging system. And these may include the transport of raw materials, the movement of empty packaging to food packaging operations, for example, and also the transport associated with the end-of-life management. So as a whole, by combining material, manufacturing, and transport that are related to impact factors, this module can support a more comprehensive evaluation of the environmental and health implications of the packaging systems across the life cycle. Now that we have known and explored a little bit the MAGNO's Ecosystem Digital Twin, let's move to a practical use case with a simulation. So just give me a sec. As we have seen during the presentation, this is our digital twin. We have selected every process for each kind of, specifically for our PET bottle of water. For example, we have already filled all the parameters. Also, some of them are the default values that we have verified within the literature. So if we go quickly through each process, we have already seen them. Here we have, we're going to model the rigid truck vehicles for to retailer transport and also to post-manufacturing transport. So if we just go to the last module and we click calculate results, the simulation, the digital twin runs directly the simulation, and it generates a comprehensive report that summarizes all the results across the entire packaging value chain. So let's see. This report is organized by life cycle stage. For example, here we have the manufacturing stage, the post-manufacturing transport, then the to retailer transport, etc. And it allows users to explore the performance of each process individually, while also obtaining the overall assessment of the packaging system. Also, for every module, let's see, for example, the manufacturing module with injection. The report provides key performance indicators such as the mass balances, the energy consumption parameters, and so on. And when relevant, of course, these results are also presented in the form of Sankey diagrams. So they act as graphical visualizations to make it easier to the user to identify the main contributors to the material losses or energy use. So as we can see here, the main contributors to the energy breakdown in the injection case is cooling, injection energy, and the reset stages. Also at the system level, this report brings together environmental and health impacts indicators, and they include life cycle assessment results, carbon footprint, and additional environmental factors such as microplastics generation and leakage to oceans and migration to food as well. So these allow users to compare different packaging designs, different materials as well, or even end-of-life strategies if we use a consistent set of indicators. So as such, overall, this digital twin and this reporting, functions as transforms these simulation outputs into actionable information, which ultimately it helps stakeholders to evaluate the alternative scenarios, and this digital twin can support data-driven decision making. So that was all from my side. Now we go to the question and answer roundtable, and yeah, it's your turn. All right, Arturo.
Yes, hi Anna. First of all, thank you for the presentation. It was very interesting. I think the interface of the platform is very user-friendly. So congrats for that to all the team. And I have two questions. Is this platform is already finished? And the second one is when it's finished, it's gonna be an open access platform or just for the partners? How it's gonna work?
Yes, thank you very much, Arturo, for your question. And this platform, the Digital Twin, is developed already. It needs some refinements, but its final version, hopefully it will be available on July. Alejandra can tell you better if it is everybody will have access to this platform or not.
Yeah, thank you, Anna. So yes, as Anna said, it's going to be full delivered in July, and it's going to be available to all partners to test their strategies. And later we will decide whether this platform is going to be open access or not, because at the end of the day, it's going to depend on a collaborative decision between all the partners.
Okay.
Thank you, Alejandra.
Thank you so much.
Yes, while.
Hi, Anna.
Hello.
Congrats for this great work. I have two related questions. Could you tell us a bit about the thermodynamic model behind? Like, are they handmade model or software based? And how are we sure about the number of input in each process? I mean, what is the logic used in order to select for each process the type and number of inputs?
All right.
Thank you.
Thank you very much. So the IDENER team has been doing a lot of research regarding all the processes that are covered in the digital twin. So all these processes have been modeled following the standard equations for these industrial processes. And for the default parameters, they have been verified through wide literature, industrial papers, and also scientific literature. So it is very reliable according also to both industry and scientific communities. Does this answer your question?
Yeah, I mean, it means like based on the literature, we have selected the number of type and type of inputs, right?
Mm-hmm.
Okay.
Yes. Exactly.
Yeah, just to quickly build on that. So basically, there are a lot of research about theoretical and engineering equations, right? So basically, the modeling part of the digital twin that you are not seeing because it's code based are based on those equations. So the inputs, the number of inputs, the type of inputs are just based on those requirements of those published peer-reviewed engineering equations.
Thank you, Alejandra.
Okay, means
Carlos,
that
go ahead.
is this kind of simulation already exist, or like we are doing something like additional by regrouping more than one thermodynamic models, increasing the number of processes to cover all that chain? Is this the essential advantage of our digital tool?
This has never been done before. So in some cases, the engineering equations do exist, but are just to fine-tune processes. But in no case have they been used to predict the energy and the material efficient in this kind of platform. And in some cases, the engineering equations do not exist at all. So for example, when Anna was showing the material balances, right, and the distribution of the different material flows, that has either not done before. So that was built upon a lot of data that we process about consumer behavior and recycling behavior in different countries. So the nuance of this digital twin is that we bring this knowledge together to output system level energy, material flows, environmental impacts. So yeah, it's completely new.
That's great. Congrats again. Thank you.
Thank you. Carlos, go ahead, please.
Hello everyone, I'm Carlos from Andaltech. Thank you for the presentation. It seems like a very interesting digital twin that you're presenting. I had a couple of questions. First, regarding multi-material packaging, if you are able to model like different layers of different materials and if they are primary, secondary, tertiary, whatever, in the manufacturing process. And secondly, if you are thinking or maybe you will integrate to input limits, for example, regarding all the regulations that are coming that are quite restrictive in terms of a percentage or recyclable material that you have to put. If you are considering like maybe some kind of signal like, okay, we are putting all these inputs in the digital model. I'm not a computational IA, whatever. I'm a lab guy, so I don't have that knowledge, but if you are able to put this limit in order to also give the perspective that we are considering all the regulations that are going to be implemented in the next years. Thank you.
Thank you very much, Carlos. Yes, we will for sure implement this, or at least think about this, since it is the path that the food packaging industry, sorry, needs to follow. So for sure we will be thinking about this. And regarding the first question about the multi-packaging strategies, yes, the multi-layer, sorry. Yes, it will be considered in further stages. This is a beta version, the initial version that we can already see all the results. So the idea is to further consider these kind of advanced types of packaging.
Perfect. Thank you very much, and thank you for the coordination for the coordinators for the proposal. It seems very interesting. Thank you.
Thank you very much. Yes, Jessica.
Hi, hello everyone. Hi, Anna. Hi, Alejandra. So it's Jessica here from DNV. I am a food technologist, so I would like to see this from the food perspective. That's why my question would be like, how did you connect the material itself with actually the food that it's packaged? Meaning, do you think of integrating some regulation regarding which kind of material that can be used that will go in contact with certain types of food, or you have already limited at the beginning the choice with certain material that we know already that are regulated and can go in contact with materials. So regarding that food safety aspect, and congrats the team. It is very user friendly, as you showed us, and very, very nicely and clearly explained. So thank you very much.
Thank you very much, Jessica. Yes, as I explained a little bit to Carlos, the food safety policies and so on will for sure need to be considered, but in further stages. Right now, the idea that we have for food products and the relationship with the packaging itself would be the shelf life. This is the information that we have regarding this, but I think it is a good idea to limit it for one type of package, that it wouldn't be recommended to be in contact with these other food products. So for sure, this is something that we will consider, and it's very interesting that you mention it.
Thank you so much.
Thank you very much. Does anybody want to ask anything else? Don't be shy.
Yeah, just to quickly comment while everyone else is trying to figure out question. Thank you, Jessica, for the comments. Just to mention to everyone that the main idea behind this workshop, doing this workshop at this time before delivering the official digital twin, is just to gather feedback from all of you. So after the workshop, we'll be sharing with you some kind of questionnaire in which we will kindly ask you just to provide further questions that maybe you didn't think of during this workshop, or further feedback that you might have, some things that you would like to see, some things that you are not sure are already in the digital twin. So in this way, we can collect all this feedback and just put it in the final version of the digital twin to be delivered in July to the European Commission. Thank you.
Thank you, Alejandra. Yes, Luigi.
Hello. Congratulations for the digital twin and the presentation. I have a question regarding the usability of the tool. What if, assuming that I'm a food producer, for instance, or let's say a manufacturer, a packaging manufacturer, what if I only enter the data referring to the stage before me, so the development and the data concerning manufacturing, but not all what is after that, because I would like to know how my packaging is performing towards the criteria that you showed. Will the simulation run, and will it provide insights still, or I have to complete all the modules that you showed?
All right, so I'm going to share my screen very quickly again. So I think I can answer you better. So first of all, sorry. Here it is. All right, you can see my screen, right? So first of all, we have two analysis modes. We have the beginner mode with simplified interface and so on, and the advanced one that we have the full control over all the technical parameters. This isn't related to your question, but I just wanted to clarify that. Then we can select between the flow type that we want to follow. So we can select the circular flow. We model the whole value chain, or we can module just a linear flow. In both cases, we can go for, I don't know, we select the manufacturing option, and we can just stay here. Maybe you can also select the end of life option just because. But yes, you can module, you can perform the simulation, just the stages that you want. And also it wouldn't be a problem if you're a food manufacturer and you just know the parameters, for example, for your module, because as I said in a previous question, we have done a deep research of the different values and default parameters. So it is a reliable simulation, just if you want to see the whole process and not just your stage. But yes, it is possible.
Very much.
Thank you. All right, so does anybody else want to ask anything else? If not, this workshop can be concluded. And thank you very much, everyone, for attending this workshop. Thank you for your interesting feedback, and I hope to see you soon. Thank you.
Thank you so much.
Thank you so much.
Bye-bye.
Bye bye. Bye.
Thank you.
Thank you, Anna.
Goodbye.
Bye.
Bye.
Thank you. Bye bye.